Okay, so now we have this general notion of a completion in which various things are given as parameters. In particular, the base type, but most of all, the absolute value that we're going to use on our base type is given as a parameter to this completion process. We said if we gave the normal absolute value on the rational numbers, we end up with the real numbers. So what if we run this completion process on the rational numbers using a different absolute value? What do we end up with? Well, depends on what that absolute value is. So the next thing we're going to do is introduce a new absolute value, which we call the p-adic norm. So the p-adic norm is actually a family of absolute values. We have one for every prime number p. Let's start by just fixing some arbitrary natural number, not necessarily prime, but bigger than 1, some number p. And we're going to start by defining the p-adic valuation. We're not at the absolute value yet. The p-adic valuation is defined as the highest natural number n, such that p to the n divides the input z. So what does that mean? It means that the valuation of some integer z is higher if more copies of this fixed number p can be factored out of z. So if some very high power of p divides z, then the valuation of z is high. If we can't divide any high powers of p into z, then the valuation of z will be low. We have to say what to do in the case of 0, because everything divides 0. So we're just going to say it's infinity, or we can just say the value is 0. It doesn't really matter for the time being. But okay, so we have this notion of a valuation on integers. Let's extend it to the rationals. So if I have some rational number in simplified terms, q over r, then I say that the p-adic valuation of q over r is the valuation of q minus the valuation of r. So that is to say, if some high power of p divides the numerator, q, then my valuation will be high. This will be a big number, and this will be 0. If instead some high power of p divides the denominator, not the numerator, then this first number will be 0. The second number will be very big, so I have 0 minus some big number, and I get a very negative valuation. Notice that p can't divide both q and r if q and r are coprime. That is, if our fraction is in simplified terms. So this valuation function we're going to use to define the p-adic norm. And keep in mind the growth behavior of this function. We said the function is big if high powers of p divide the input. So the norm is going to have the opposite kind of growth behavior. We say that the p-adic norm of some input x is equal to 0 if x is 0. Remember, that was a defining property of an absolute value, by the way. Otherwise, if x is not 0, then we take the valuation of x, we take p to that power, but then we invert it. Take 1 over p to the valuation of x. So what's the growth behavior there? Suppose that x is some rational number, and suppose that a very high power of p divides the numerator of x. So the valuation is very big. That means that p to the valuation is very big, but 1 over a very big number is very small. So if a high power of p divides the numerator of x, then x has very small norm. In the other direction, if a high power of p divides the denominator of x, then we have a very negative norm, which means we have a very negative valuation, which means p to the valuation will be very small, which means 1 over that will be very big. If powers of p don't divide the numerator or the denominator of x, then we just get something close to 0. We have 1 over some smallish number, but not tiny, 1 over p, let's say. So this is the p-adic norm. Let's see some examples just to make it a little more concrete. And here we're going to look at the 3-adic norm. We're going to fix our number p to be 3. So if x is 1, 3 doesn't divide 1, which means our valuation of 1 is 0. That means that the norm of 1 is 1. The 3-adic norm is 1. What if x is 3? Well, 3 to the power 1 divides 3, but 3 to the power 2 does not divide 3. So that means our valuation has to be 1. The biggest number is such that 3 to that number divides 3. And that makes the 3-adic norm 1/3. 1 over 3 to the valuation. 6 is the same. So that's interesting. Under the p-adic norm, 3 and 6 have the same size. The size of our numbers are measured somehow by the number of copies of 3 that we can divide into them. 18 is an even smaller number. We can get more copies of 3 into 18. So 18 is divisible by 3 squared, gives us a norm of 1 over 9. Well, what about 1/3? So now we have something in the denominator. Remember, if 3 divides the denominator of our rational number, then we get a negative valuation, which means we're going to get a norm that's bigger than 1, in this case 3. And then, well, here's a really big power of 3 that gives us a valuation of 10. So this number is a big integer, but it's tiny in the 3-adic valuation. This number is 1 more, previous number plus 1, but 3 doesn't divide this number at all. So our valuation is 0, our norm is 1. Even though these two numbers look close, in fact, in the 3-adic norm, they're fairly far apart. So you can try to compute some more examples of this if you're not convinced by this demo, if you really want to see how these functions scale. As you might expect, this p-adic norm, because we were talking about absolute values, the p-adic norm should be an absolute value, and when p is prime, it is. If p is not prime, actually the calculations we have to do don't quite work out. So from now on, we're only going to consider prime values of p, in which case you can try to sketch the arguments yourself. They're not very tricky. The p-adic norm is indeed a generic absolute value, as we defined it in the last video. Well, if we have a generic absolute value, we can throw it into our completion machine, and we should get some new type out of it. The quotient of the Cauchy sequences of rational numbers with respect to this new absolute value, which we call the p-adic norm. The result of this we call the p-adic numbers, which you write like the rationals q, but with the subscript p. This can be a little bit misleading because, well, the p-adic numbers are kind of more like the real numbers than the rationals, right? We started with the rationals in both cases. We got the real numbers with one completion. We got the p-adic numbers with another completion. But for whatever reason, we write them as QP. So that's the definition of the p-adic numbers. The definition alone isn't particularly useful, right? We want to know how these things behave. What can we do with them? So let's look into that a little bit. And again, I want to do this by analogy with the real numbers. So a real number officially is a Cauchy sequence of rationals, or an equivalence class of Cauchy sequences of rationals, blah, blah, blah. But in practice, we think of a real number written out in decimal form, right? Think of it in base 10. And it's a right infinite sum. What do I mean by right infinite? I mean that if we're writing out a real number, we start with the leftmost digit has to be some finite number of places left of the decimal point. We can't have a real number that has infinitely many values left of the decimal. But it can have infinitely many values right of the decimal. For example, 3.333 repeating. It's finite to the left, but it's infinite to the right. And represented mathematically, this is a sum from negative infinity to some finite, maybe negative, maybe positive integer k, of coefficients, ai, which are digits, times powers of 10. So the ones place, the tens place, the hundreds place, etc., all being summed up here. For the p-adic numbers, we can use a similar representation, but with a couple twists to it. So first of all, instead of thinking of this in base 10, like we typically do for real numbers, let's think of it in base p. Instead of our coefficients being in 1 through 9, they're going to come from 0 to 9, they're going to come from 0 to p minus 1, looking at powers of p instead of powers of 10. But more interestingly, instead of being right infinite, like a real number, p-adic numbers are going to be left infinite. I pick some spot, k, which is right of our decimal point. Well, it could be left of our decimal point too. It's right or left, but some starting point, k. And then we keep adding things to the left. We keep adding bigger and bigger powers of p instead of smaller and smaller powers of 10, like we did for the real numbers. So you have an infinite sum from k to infinity of higher and higher powers of p, with coefficients coming from 0 to p minus 1. So we said that this is right infinite. If we wrote it out like we write out a decimal number, we'd have some finite number of things right of the decimal point and infinitely many values left of the decimal point. So that sounds weird, right? How can that be a number that should be infinite? But remember, we're not working with our standard norm anymore. We don't have our usual absolute value. In the p-adic norm, that number is actually finite. It has finite norm. And why is that? Well, I add higher and higher powers of p to it, but remember that the higher the power of p that divides a number, the smaller the norm of that number is. If I add something times p to the 100, well, then the norm of p to the 100 is really, really small. So it doesn't actually grow the number to keep adding these higher and higher powers in the way that it would grow a real number. So pretty weird, right? To make this a little more concrete, let's try to do some arithmetic on these sequences. So here we have the p-adic number that is just all 4s, infinitely far to the left, a stream of 4s. Below that we have the p-adic number 1. So if we want to think of this as an infinite stream, everything to the left of the 1 is 0. Just like a decimal number, it can always be 0.0000, etc. How do we add these together? We do a kind of carrying arithmetic. So 4 plus 1 gives me 5. We're working in base 5 because we're doing arithmetic in the 5-adic numbers. So in base 5, we represent 5 as 1, 0, which means 4 plus 1, I write down a 0, and I carry the 1. So now I have 4 plus 0, but there's a 1 carried, so that gives me 5. Again, 5 is really 1, 0, so I put a 0 at the bottom, carry the 1, and we're in the same place. Still 4 plus 0 with the 1 carried, so on and so on. I'm going to get an infinite stream of zeros at the bottom here, which means repeating 4s plus 1 gives me 0. This repeating 4s thing at the top is kind of like negative 1. It's the additive inverse of 1 in the 5-adic numbers. How about multiplication? Here's another p-adic number. This is repeating 3 1s to the left and then a 2 in the unit spot. And let's multiply that by 3. Well, 2 times 3 is 6. In base 5, 6 is 1, 1. So let's put the 1, carry the 1. 3 times 3 is 9. But I carried a 1, so that gives me 10. 10 in base 5 is 2, 0. So I can put a 0 at the bottom, carry the 2. Now I have 3 times 1 is 3, plus 2 is 5, which is 1, 0. So 0 at the bottom, carry the 1, rinse and repeat. I'm now at 3 times 3 plus 1, and we see the pattern. We're going to get an infinite stream of zeros at the bottom, which means that this funny thing at the top times 3 gave me 1. This is the multiplicative inverse of 3. This is like 1/3 in the p-adic numbers. It's a weird way to write 1/3, right? But it has the property that if I multiply it by 3, it gives me 1. And then as one more example, just to try out, what if I take these two numbers at the top here and just try to add them together for fun? Well, again, we can go through the base 5 arithmetic. I won't do too much of it. 4 plus 2 is 6, so that's 1, 1. Put the 1, carry the 1. 4 plus 3 is 7, plus 1 gives me 8, which is 1, 3. So put the 3, carry the 1, go on and go on. We end up with this repeating thing at the bottom. But that makes sense, right? Because over here we said that repeating 4s was like -1. So I've added -1 to this thing at the top, and I've just taken 1 off of the unit spot. So yeah, it's like I subtracted 1. So it's a weird kind of thing to wrap your head around, but the rules of the game are not all that tricky. Maybe the most confusing part is how we actually got to this from this abstract notion of a Cauchy sequence completion. And that's maybe a deeper topic for another day. Another interesting thing, though, that I wanted to point out about the p-adic numbers is how we think about distance between them. So if we think of the p-adic numbers, and here I'm going to ignore things to the right of the decimal point for the moment. I'm only going to look at infinite left streams starting at the decimal point. We can basically group p-adic numbers by their initial segments, so by their rightmost segments. This top branch up here, this has all the p-adic numbers whose units place is 0. So everything that starts with the 0 on the right. Here's everything that starts with the 1 on the right, everything that starts with the 2. Every p-adic number of the form that I've described has to be in one of these branches. And if we try to group things together, well, we can group them by how many initial digits they share. Everything in this group up here, these should all be closer to each other than they are to things down here. Anything that's in this subgroup, things that start with 2 zeros, these should all be closer to each other than they are to the things that start with 0, 2. But these things at the top are closer to these than they are to these down here. So to figure out how close two p-adic numbers are, and really a p-adic number is like an infinite path through this tree. So if I have two infinite paths through this tree, to figure out how close they are, I need to backtrack to the right until they have a common node. And the depth of that common node tells me how close those numbers are. So if you've done some math, this basically gives us a topology on the p-adic numbers. If that word doesn't mean anything to you, it's okay. But it gives us a notion of closeness. In fact, we don't need to stop at a notion of closeness. We can get a notion of distance or size, like an actual measure of how close things are, if we take the p-adic norm that we defined on the rational numbers and we lift it to the p-adic numbers. There are technical reasons why we're able to do this that, again, are not so important now. But the idea is that we get an absolute value on the p-adic numbers that behaves a lot like the p-adic norm behaved on the rational numbers. In particular, there's this really weird property to it. This is actually one of the most fundamental notions about the p-adic numbers. The norm that we have on them is non-Archimedean. If I have two p-adic numbers, x and y, and I add them together, the sum can't be bigger than either x or y. So we can't add things together and get something bigger. This is not the case with the real numbers, right? If I add together 3 and 5, I get 8, and 8 is bigger than 3 and 5. But with the p-adic numbers, we can't do this. We can only grow in size, so to speak, by multiplying things together. So I think that this is counterintuitive, and you might even think, why does this work? How can an absolute value, how can a norm have this property? But the rules that we wrote down for an abstract absolute value, they don't prohibit this. It's completely allowed. It's not required, but it's possible. And the fact that the p-adic numbers actually have this property, that the p-adic norm does, makes certain things about the study of the p-adic numbers very convenient. In particular, it makes doing things like calculus very well behaved. And this is why a lot of mathematicians use the p-adic numbers for various properties. If you can take a question about the real numbers, maybe something calculus related where you have continuous functions, but they're not quite continuous enough. If you can translate that to a question about the p-adic numbers, then you get a much better behaved notion of continuity, basically for free, because the norm is more powerful in this way. And so if you can translate your question correctly, somehow it can become more tractable. It can be easier to solve. There's another important property, or a consequence of the non-Archimedean property of the norm. If I have two p-adic numbers that are each of norm at most 1, then if I add them together, their norm is still at most 1. By generic properties of the absolute value, the same holds for multiplication. If I multiply x and y together, then the norm is still at most 1. So what that means, if I take the set of all of the p-adic numbers whose norm is at most 1, then it gives me a ring. It's closed under addition and multiplication. That is, I don't really need to think about anything outside of the set. I can add and multiply these smaller p-adic numbers together as much as I want, and I never escape this sort of condensed set. So we call this set the p-adic integers. And so depending on what we're trying to do as mathematicians, we may want to use the integers, we may want to use the full p-adic numbers. The final result here, and I present this mostly because this has been formalized in Lean. It's a nice result to end on, and I'll show you some Lean code in a second. Hensel's lemma is a nice kind of fundamental result about polynomials over the p-adic integers. It says that if I have some polynomial function whose coefficients come from the p-adic integers, and I have some value a, which is a p-adic integer, that satisfies some basic property, then there has to be a root of my polynomial that's within a certain distance of a. So this is, I mean, in some sense, it's just kind of a random result, right? It doesn't necessarily have a deep meaning. But the same kind of thing definitely does not hold if we're looking at, say, polynomials over the integers. There's something special about the p-adic numbers that gives us extra ability to do this kind of, well, in this case, root searching. It's like basic calculus. That's just not available in more traditional types. So why did we bother with any of this at all? There's nothing special for us as computer scientists about Hensel's lemma, necessarily, or even about the p-adic integers in general. But the point of this whole lecture was to show that, well, like, real mathematics can be done in Lean. It's not all program verification and concrete things like integers and rational numbers. We can define kind of what seem like random abstract mathematical things like the p-adic numbers, prove abstract theorems like Hensel's lemma. This is all doable, and it's done. This is one little piece in a huge realm of possibilities. And in fact, this development of the p-adic numbers has been used in further, more complicated developments. So it's not a standalone thing. So, okay, I mean, I say this, but I haven't actually shown you any Lean code about this yet. I showed you the beginning of the completion code. So maybe it's time to switch from the slides and look again at VS Code to see how the p-adic numbers were actually developed.